covering a couple of sessions. One is first session is NVIDIA accelerated computing, and the next session will be on scheduling a multi-node job with SLURM, right? So with first session, we'll cover NVIDIA accelerated computing. In this session, we'll get into a accelerated computing overview, and then quickly discuss a SuperPOD reference architecture and how it helped to build a cluster like AIRAWAT-PSAI, right? And then we'll quickly look into NVIDIA deep learning stack, especially specific to LLM and speech, and then quantum computing, and then Modulus, right? Then we'll look into NVIDIA HPC stack and few case studies, how research institutes and enterprises across globe using DGX, and also specific to C-DAC, how this has been leveraged, right? So these are the complete agenda of today's session. With that, we'll start with accelerated computing, right? So we know that accelerated computing uses specialized hardware like GPU to parallelize a certain portion of application, right? So in case of scientific computing, a certain portion of application will be parallelized, and in terms of AI, like pretty much most of the workload is parallelizable, right? So if you think of AI from the Alexian movement till now, like the workload is evolved huge, right? Currently with LLMs, we need huge compute, and especially with HPC from the point CUDA's introduced until now, there are a lot of changes in terms of workload and complexity, right? Which demanded huge compute, especially with GPUs and the scale up and scale out compute we have, right? Huge clusters we have, right? All the use cases specific to AI or scientific computing, we are seeing huge demand for compute, and also the workload demands a huge clusters kind of setup to run your workloads, right? So that's the primary reason why the evolving workload nature of both AI and scientific computing is driving the accelerated computing where we are in today, right? So especially with accelerated computing combined with AI, we are getting a million x speed up, especially to power and scientific computing, right? For example, if you see a single threaded application, it is not evolving at the speed where it used to be, right? Because of limitations it has with CPUs, and Moore's law is getting challenged, right? When you see GPUs using a specialized hardware to accelerate a portion of a workload, we are seeing huge leaps in terms of performance, right? Especially with HPC combined with AI, you are getting million x speed up. We'll see why this kind of perform speed ups is achievable with an example, right? So accelerated computing is three major motors of the current technology, right? One is starting with accelerated computing. Number two is scale up and scale out. Number three is combining AI to accelerate the workload, right? So earlier, if you see in 2006 when CUDA was introduced, we are able to see in a single GPU or single node system, we are accelerating a certain portion of application which is parallelizable in nature, and rest of the things will be running on a CPU, right? This is a point where CUDA was introduced in 2006, and from there we are seeing huge acceleration being used in HPC workloads. But if you think of next layer, where you're seeing from 2010 when AlexNet was introduced, we are seeing a scale up and scale out compute, right? Basically clustering huge systems into single node and able to scale into multi-node workload, right? This helps from AI standpoint, helps us to create a huge multi-node task and able to train a large model, especially in the current scenario. Like LLMs every LLMs demand a huge compute, right? You need to scale to multi-node and able to pre-train, fine-tune, or even do the prompt engineering, right? So this is how earlier it's just a single node system or single GPU workload, but when AI was introduced, now we are getting into an entire data center unit as an accelerated unit. Like for example, the AIRAWAT-PSAI, you can consider the entire unit as GPU accelerated, right? You can easily train a huge large language model with the entire cluster with scale out and scale up performance. On top of it, so now we have seen two layers, right? One is accelerated compute, number two is scale up and scale out, right? We're considering the entire cluster as a single component unit. And third important engine is AI, where if you integrate AI to solve scientific computing problems, you are seeing a million x speed ups in terms of entire performance, right? We'll see example how this is happening. So here, if you see when accelerated computing was introduced, especially CUDA was introduced. So basically this CUDA is used to program like libraries like NAND to create accelerated molecular dynamics, right? In 2006, UIUC accelerated NAND with GPU, where they could simulate 1 million atoms in 20 nanoseconds. Basically, you can simulate 20 million atoms in 20 20 nanoseconds, right? That's what happened when CUDA was introduced. Now in 2020, if you see similar level of with similar acceleration and how the scientific or the accelerated computing has been evolved, we could see 1 billion atoms have been simulated using with 500 nanoseconds, right? So this is a huge improvement in compute, which is 1 million times larger compared to the entire years of acceleration computing, right? So if you compare this with Moore's law, Moore's law is just given 1000x performance increase. With when you compare this with accelerated computing, we are getting 1 million times larger throughput compared to earlier versions. And this million x speedups is especially possible because of integrating AI with simulation workloads, right? For example, the researchers at San Diego University has started using AI to simulate a coronavirus and to visualize the coronavirus protein, right? With combination of AI, they're able to see million-fold X performance when they were able to simulate this COVID-19 virus, right? So all this 305 million proteins have been simulated in a 20 nanosecond fashion. So this gives you the huge performance leaps compared to just using a CPU-based cluster, right? With accelerated computing, with scale up and scale out compute, and with combination of AI, we are able to see the million X speed up. So that's one of the primary reason why compared to typical CPU based clusters, clusters with GPU has been giving huge performance leaps compared to any workload for that matter, right? If it is a HPC simulation workload or a AI workload. So this massive leaps in performance is especially due to combination of NVIDIA's end-to-end software stack, right? So if you see in the left panel, you can see from over the years, from 2016 when first DGX was introduced with P100, we are getting 26x performance increase in last 6 years. Compared to, if you compare this with Moore's law, like especially with CPU, you see that is just 8x increase, right? So this benchmarks, especially based on MLPerf industry standard benchmarks. If you see, both the clusters or a machine used for this benchmarks are a 8 chip clusters. Basically, with if you think of a DGX, it has 8 A100 GPUs, and especially with Intel cluster also, it has 16 Intel CPUs, right? So especially in the middle panel, you can see MLPerf benchmark, like where we are training BERT on a CPU cluster and on a GPU cluster, GPU DGX machine, right? Both you can see there are 20x, 27x performance increase compared to CPU based cluster. And in the right panel, you can see two primary benefits, right? One is the net zero emission, and number two is the lowest total cost of ownership, right? So if you think of CPU cluster to run this workload, right, especially the inference workload for this kind of BERT or transform based model, we have 10x reduced number of nodes required if you have a GPU acceleration, right? And in terms of cost, you can see 15x reduction in cost. So overall, if you consider the emission, which is net zero, and also the total cost of ownership, which is giving huge total cost of ownership benefits, right? With the performance increase of 26x. That's what the entire end-to-end stack, along with infrastructure like DGX, helps you to achieve. So, so all this million X performance speedups for AI and HPC workloads and this 26x performance improvement is the base layer for this is all these chips, right? Which NVIDIA introduced, starting with GPUs and then DPU. When you think of data center as a compute unit, DPU plays an important role there, right? Which is data processing unit, offloading all your network processes into the specific chips instead of making CPU to handle those, right? And especially with CPU handling all the input and output operations with all these huge clusters, right? All these three chips layer a base foundation for getting this full stack performance, right? Again, so to reiterate, the entire performance increase is only because of the end-to-end stack which NVIDIA offers, right? So in earlier slide, we discussed the basic chip layer where it has GPU, CPU, and DPU. And then next is on top of it is a server platform layer, whether it's a DGX server or it's a RTX or HGX server, or even instance in cloud, or it's a SuperPOD cluster, right? All these chips are well integrated and built for the specific appliances to address specific use cases, right? On top of it, you have system level libraries or acceleration libraries to help you to accelerate all the workloads through these GPUs. And on top of it, you have platforms, whether it's NVIDIA AI, which include all the AI SDKs, which helps you to build an end-to-end workflow for use cases like conversational AI or building a large language models. And you have a NVIDIA Scientific Computing SDK, which offers you all the HPC libraries and math libraries to accelerate the workloads, and Omniverse for digital twins and simulation kind of workloads, right? So all these layers, starting with the underlying layer of chips, GPU, CPU, on top of it, server layer, on top of it, acceleration libraries, on top of it, platforms, on top of it, SDKs, helps you to build an end-to-end stack. With this end-to-end stack, you can accelerate workloads in AI, HPC, or even with a digital twins, right? So all this performance increases not just because of the hardware, but with the end-to-end ecosystem which NVIDIA built. So we'll deep dive into each of this layer and see what are the SDKs available for you and how you can start using it. And in the sessions in the subsequent weeks, you can deep dive into each of these SDKs and help you to start using these SDKs. So yesterday you have seen we have discussed about DGX 800. I'll just quickly spend a minute to reiterate on that. So basically DGX 800 is a compute unit of your AIRAWAT-PSAI cluster, right? So all these workloads are running here with 8 840 GPUs available with the system. But this system is a single compute unit of it, right? But how this system is able to scale to multiple nodes and giving you performance without any bottlenecks, right? That we'll discuss how this is possible with NVIDIA SuperPOD reference architecture. And what is special about this GPUs, right? Especially with the 800 GPUs, which you have with the Paramsiddhi cluster, right? One is, of course, the GPU memory, which is compared to earlier version V100, we have 40 gig memory here, so we can load larger models. And on top of it, we have a third generation tensor core, which is specially introduced in 800 GPUs to handle tensor operation, right? This gives you 20x performance improvement compared to the latest earlier version, which is Volta architecture, right? And also to give you more flexibility, we have multi-instance GPU, but this comes to picture when you have looking into the cluster from an instance standpoint, right? So in future, if you're getting inference infrastructure, multi-instance GPU is going to make huge impact in terms of flexibility and delivering huge performance for inference. So as I discussed, tensor cores is one of the specialized cores introduced in 800 GPUs. So basically, this course helps you to get a 20x performance throughput compared to the earlier version of V100 GPUs, right? This is because of Tensor Core, which can handle the tensor operations efficiently. Especially tensor operations are major workload in AI workflows, right? So on top of it, there are also specific precisions introduced in TensorFlow, tensor cores. One is instead of FP32, you can start using BF16, or you can also use TF32. So these kind of precision would give you much more performance improvement compared to a typical FP32 or FP16 precision, right? You can start using this when you're training your model in 800 GPUs. That is special about 800 GPUs overall, right? So when you think of performance, especially with DGX 800, you can see all the huge performance increase compared to the earlier versions, especially with recommender system training, right? You can see 3x throughput if you're using DGX, right? But in our case, we are using 320 GB of overall system memory, GPU memory for DGX 800, right? So we are getting a 1x improvement in terms of compared with DGX2, which has V100 GPUs, but it is a 16 GPU there, but in 800 it's just 8 800 GPU. And also from an inference standpoint, you can see that especially DGX 800 320 GB, if you compare a MIG slice of 7 GB GPU, you can getting 1x throughput compared to the earlier version of V100 GPUs, right? V100 doesn't have a MIG, so you don't have the flexibility of slicing a GPU and able to deploy your models. In that case, it offers both flexibility and performance here. And then if you think of a big data analytics workload, you're also getting a 2x faster execution of queries, right? This benchmark is based on 30 queries done on 1 TB of data set, right? So compared to DGX1, we are getting 2x performance improvement in DGX800 with 840 gig of GPU memory, overall 320 GB of GPU memory. And if you think of 80 gig 640 GB of GPU memory, you're getting 8x performance improvement from all the front, whether it's use of flexibility or the performance. DGX ended giving you a huge performance leaps and increase in compared to the earlier version. So next we'll look into DGX SuperPOD, a reference architecture which helps or which used as a reference to build a cluster like AIRAWAT-PSAI, right? And what is special about this reference architecture, and how this well interconnected architecture helps you to build a seamlessly scalable compute infrastructure, so that none of the components acting as a bottleneck. So basically, NVIDIA DGX SuperPOD is a modular architecture which has a reference to connect huge nodes of DGX 800 with high-speed interconnect and storage, right? Basically, this is well tested and proven by NVIDIA, so that you can easily replicate this reference architecture across building a similar kind of huge compute infrastructure, right? So this is exactly make sure that you get a easily scalable infrastructure and high availability, and also in terms of performance, there is no bottleneck between this components, right? So basically, in Paramsiddhi, Airavat Paramsiddhi case, we have 82 nodes. So basically, we have 4U DGX SuperPOD, right? Basically, a single SU consists of 20 DGX nodes. So in our case, we have 4 SU, basically 80 DGX nodes, and a couple of nodes acting as a login nodes for you to log into this cluster and able to spin up your jobs, right?
Hi, Ian. Sorry to cut you here.
Yeah.
We can still notice that your voice is breaking, even though we try to fix from back end. Can you try to shift your location? Or just try to connect it from different headset, or try somewhere else, please, because we can still hear that your voice is getting fluctuated.
Okay, is it breaking or is there a background?
No, there is no background noise. It's just that your voice is breaking.
Okay. Yeah, I'll just give me a minute. I'll check it.
Yeah, sure.
Hey, hi Meghna. Is it okay now?
Yeah, I think it's better now.
Okay.
Yeah.
Thank you. Yeah.
Thank you.
Okay. So let me on the SuperPOD architecture built by NVIDIA and tested by NVIDIA, so that similar kind of compute cluster can be built and replicated for customers, right? So this is a combination of all compute, storage, and network, so that you can seamlessly replicate the similar infrastructure at customers' environment, right? Basically, that's the purpose of SuperPOD reference architecture, so that you can replicate the cluster with a high availability without issues with any components, without any bottlenecks between these components, right? So that's the basic idea of building this DGX SuperPOD reference architecture. So as I mentioned earlier, there are three major components in this reference architecture, right? One is compute. So all our DGX machines are compute. And then the storage, the high-speed flash storage we'll have with this cluster. And then the network, right? All this InfiniBand interconnects, high-speed interconnects, acting as a communication layer between this compute cluster, right? So all these three components are well interconnected, so that there is no bottleneck between each of these components. Without that, you can easily scale your workloads across these nodes without any challenges or bottlenecks happening in network or in storage, right? That's the primary reason NVIDIA SuperPOD reference architecture, which is tested by NVIDIA team, which can be easily replicated at customer ends, right? So even AIRAWAT-PSAI is using similar reference architecture, so that you can seamlessly scale your workloads across multiple nodes without any bottleneck in network or in storage. So as I discussed earlier, this what is reference architecture is considered as a scalable unit, basically a single scalable unit of 20 DGX node. So in our AIRAWAT Paramsiddhi case, we have 4 SU, basically 80 DGX nodes, and 2 nodes acting as a login node. So next we'll look into NVIDIA deep learning frameworks and tools. What are the complete set of SDKs available, and we'll touch base few SDKs in detail, so that we can see how this can be leveraged, right? Before that, if you have any questions, I can take it up. Meghna, we can take up few questions, right, on chat.
Yes, sure. So please feel free to post your questions, and we can answer. At least if not Aryan's, maybe someone else from the team can answer, since he is explaining.
Yes. Yeah, I can wait for a couple of minutes. If there is any questions, I'll address. If not, I'll resume with the session.
I guess there's a question, Aryan. Maybe you can answer, you or anyone from your team.
No, I think Paramsiddhi currently doesn't have a DPU because DPU is basically a chip at a network end, right? So it comes with a network interconnect. So currently it doesn't have, but in future you'll definitely, when you're scaling this cluster, you'll get one. Yeah, so this section is around discussing all the end-to-end NVIDIA stack and introduction to it. In upcoming sessions, we will cover similar applications. Can you give a reference links? Sure, I can share some reference links after this session in the chat. You can have a look. Yeah, or you can just search MLPerf benchmarks and NVIDIA GPU performance benchmarks. You can easily get those links. Yeah. Okay, so Chaper Rapids comparison, what was the memory in both the system? So basically the underlying rule for MLPerf is having a 8 chip nodes, right? So NVIDIA we had 8 800 GPUs, and Intel was using 16 Chaper Rapids processor for this benchmarks. I'll share the MLPerf link, you can have a look. Yeah. Great. I can take up more questions after completing this section, so we can continue with the session. So next, we'll look into NVIDIA deep learning frameworks and tools, especially what are the end-to-end SDKs we have, and what is the workflow acceleration each of these SDKs is offering for us, right? So first, as I discussed earlier, it's not just about SDKs or hardwares, right? It's an end-to-end computing platform, right? So if you see here, like from underlying hardware technologies, servers, and acceleration libraries, so NVIDIA built developer toolkits, application frameworks on top of it, right? Which helps you to accelerate workload specific use cases. For example, data analytics, we have Rapids. For AI training, we have TensorFlow, and also for HPC, we have HPC SDK. On top of it, NVIDIA also built application frameworks which helps you to address specific use cases. For example, smart city of Metropolis, where you can build all the IBA applications, real-time applications for video analytics. We have Riva for conversational AI, and also we have Merlin for recommendation system and Clara for healthcare. Like similarly, we have application frameworks built on top of this hardware acceleration libraries and developer toolkits layer, which helps us to accelerate our workflows instead of we building everything from scratch. You have a well-built frameworks for you, which you can leverage and build applications on top of it, right? So pretty much all the enterprises are using these frameworks to build the application on top of it and also deploy it in production. So all this is a seamless integration. Whether you're using training on-prem, you can easily deploy the stack and replicate it on the cloud or on the edge devices also. So all this platform is pretty much seamlessly integrated. So when you're thinking of SDKs or frameworks, so we can think of a typical AI pipeline, right? Right from development till deployment, right? So if you see in development, we have data processing, model training, and model optimization as the common workflow. Each of this workflow has a specific SDKs built for it, right? For example, data processing as DALI, which helps you to accelerate your data processing with GPUs, whether it's a audio or video, both the data can be accelerated. For NLP, it's still in progress, right? And especially for model training, for each of the use cases, we have specific SDKs built for, right? So TAO typically is a train, adapt, and optimize, the basic toolkit for transfer learning. Whether you are transfer learning with a computer vision model or NLP models, it's available, right? And Nemo framework, especially built for large language models, where you can train a large language models in a distributed fashion and also deploy it in a distributed fashion, right? It offers flexibility in terms of scaling your model training to multiple nodes and also deploying with multi GPU or multi node workflows. And then you have a Megatron LM, which is open source research for training a huge models like GPT and BERT into multiple nodes, right? And Riva for conversational AI. Similarly, if you think of a deployment flow, like especially for inference serving, we have a deep stream for intelligent video analytics workflow, and we have Riva for conversational AI workflow, and Triton inference server, where you can pretty much deploy any model and deploy in whether in on-prem or cloud, right? And also TensorRT for optimizing your model and deploying it more efficiently, right? So if you think of an end-to-end pipeline, NVIDIA is offering various SDKs and frameworks to help you to accelerate your development workflow. We'll quickly look into specifically Nemo, because that's more catered to large language models where a lot of current research and workflows are happening. And then we'll also discuss few HPC specific SDKs and toolkits. So starting with LLM and speech tools and frameworks, the primary framework comes to mind is Nemo framework, right? Which is specifically targeted for training large language models, and also it has ASR and TTS models also in package, right? So it's an end-to-end toolkit or a framework, you can say, where you can train your model, you can optimize your model, and you can also deploy the model with Triton or even with Riva, right? So basically, it offers three components. One is ASR and NLP, now currently LLM, and then TTS, right? So all this is the backend is core PyTorch and PyTorch Lightning. So the best part is you can easily scale your workloads, whether you're training in multiple nodes with Nemo without building a lot of things from scratch. You can easily use the config file and just play with the config file and train models like GPT and BERT on transfer based models, right? And also it offers a lot of ASR and TTS models. It offers 8 ASR models and also offer a lot of NLP and LLM models, right? Basically, what it offers is help you with the workflow acceleration, so that you don't want to build anything from scratch. You can just use the config file and bring in your own data set and able to train this model across multiple nodes, and also export this model in a Nemo format and deploy it in Triton or in Riva. So you can easily get the Nemo container in NVIDIA NGC. We will cover NVIDIA NGC in the next session in detail, how we can download this containers and start using it in your C-DAC cluster. So another important framework or toolkit for LLM and speech is Riva. So basically, Nemo is for training and optimizing your model. But for deploying an end-to-end pipeline, that's when Riva comes into play, right? Riva is an end-to-end pipeline framework for deploying your or building your end-to-end conversational AI pipeline, right? Right from ASR and having your LLM and NLP component, and then having a TTS component, right? All this end-to-end pipeline is can be built and deployed using Riva, right? One is the specific features it offers is highly customizable. You can train the models or customize these models, and then pretty much GPU accelerator in real time, and you can easily scale into multiple GPUs, and you can deploy it anywhere, right? Whether it's on-prem, all cloud infrastructure, or even edge or embedded infrastructure, right? So pretty much you can train the model in Nemo framework and deploy the model NLP models in or LLM models in Riva pipeline, right? So on top of it, Riva pipeline also offers ASR and TTS, so that you can build an end-to-end conversational AI pipeline. On top of Riva, you can also integrate Omniverse with digital avatars, where you can integrate avatars like characters, so that you can deliver a digital avatar conversational AI. Like most of the enterprise now are looking to deploy a digital avatar with a conversational AI backend, right? Pretty much a lot of this use cases are powered by Riva in the backend. And few more additional things are you can optimize it to a domain specific speech. Usually it is not very effective when using cloud services, right? But Riva offers you much more customizable options, so that you can optimize domain specific speeches and word boost your domain specific words, so that you can easily make sure you get a better accuracy. So currently most of the use cases have benchmark accuracy of 95%. So you can easily use this models off the shelf and able to train this, right? On top of it, for we have a support for ASR in Hindi, and we also support for TTS in Hindi, right? So a lot of Indic languages also started incorporated in Riva nowadays, and you will see slowly more languages have been added to this stack. So as I discussed, right? So Nemo framework and Riva work in tandem, right? Because for you need Nemo to train the NLP and LLM components, and you need Riva to deploy a end-to-end pipeline, right? Pretty much, it's solving a lot of use cases like contact center AI, or building a digital avatar for customer-facing digital avatars, a service desk digital avatars using Riva SR. We are seeing huge tractions. Enterprises are using Riva to deploy use cases like chatbot, a front desk, digital avatars. And one of the primary reason is the support for languages it has. It has English, Spanish, Mandarin, Hindi, Russian, German, and French, right? Pretty much common languages it's supporting, and adding more support for new languages, right? So that's one specific thing. And then the performance, right? Compared to the other cloud services, it gives you much more performance increase in terms of accuracy, because of the fine tuning it offers, right? So especially if you think of industry specific jargons, especially in sports or news, right, you need to optimize it for specific jargons, right, where it helps you to optimize the model and picking up the accent and dialects which is specific to the use cases, right. So that are the primary reason Riva is highly used, and also the performance it offers, right, 300 milliseconds interactive speech app, right, so in real time. So this is a huge requirement when you deploy a real time conversational AI pipeline, right. And then the scalability it offers, right, and then the run anywhere options, so you can train it on prem and deploy it on cloud or on prem or even on edge. So that's the primary reason you can start leveraging Riva for building an end-to-end conversational AI pipeline. So till now, we have, from AI standpoint, we have seen one specific SDK specific to LLM and speech tools. So a lot of computer vision SDK will be covered in subsequent weeks, especially for deploying a facial recognition system and training a facial recognition model. Next, we will look into briefly about quantum computing, like how this supercomputer, especially DG supercomputers, are helping in quantum computing research, right? So one of the primary reason here NVIDIA is working with quantum computing is we are seeing how today's supercomputer can help to build a quantum computers, right? The primary reason is two areas. We are seeing a lot of areas where this supercomputer can help to accelerate the workflow in quantum computer research, right? Two primary areas is quantum circuit simulation, and number two is building a tools for hybrid classical quantum application, right? Basically, when you combine this typical classical supercomputer with quantum computer, you need tools to combine this and build hybrid applications, right? Those are the two primary areas where currently these supercomputers are used for, right? We'll see what is the SDKs available for this to do this, but with quantum circuit simulations, we are seeing huge potential of GPU acceleration. Primarily, this to answer these questions like what quantum algorithms is highly effective and gives quantum advantage, and what are the requirements which we can get the quantum advantage, right, and what are the quantum processor architecture can be best suited so that we can realize the value of the applications, right. So these are the primary three questions we are trying to address with the quantum circuit simulation accelerated by GPUs, right. And then number two area which I discussed was building a tools to integrate classical supercomputer with quantum computer to get a hybrid environment so that you can carry out a lot of workloads, right, especially with quantum computing research. One question we are trying to address is how we can seamlessly build a EC tools so that you can integrate the HPC system with the quantum computers in an optimal way so that you can accelerate the workflows with the current computers at the same time researching about the quantum computers, right. So how you can make use of accelerated classical computing to solve this difficult computational problems, right, and how we can make these tools easy and seamlessly accessible for the researchers, right. These are the two primary areas, and this is the common challenges we are trying to address with the current supercomputers to address the research challenges with the quantum computers. So when you think of quantum circuit simulations, currently two tasks or approaches we are trying to accelerate with GPUs, right? And NVIDIA also felt these two tasks is very effective when you're using GPUs for acceleration. One is state vector simulation, and then tensor network, right? These are two primary approaches we are seeing, which can be hugely accelerated with GPU in the current scenario. So first is state vector simulation. So basically, this helps you to maintain a 2 power n cubic vector state in a sequential manner so that you can easily accelerate it using GPU, right? But there is a certain challenges to this state vector simulation, right? Basically, it cannot go beyond the limit of 50 qubits, right? That's when tensor network approach comes in. So it supports state vector simulation basically with the flexibility of dynamically playing with this qubits, right? And it can easily scale because of the tensor operation it has. So you can scale to hundreds and thousands of qubits and practically with quantum circuits. So how these two tasks is possible, right? To try out these two tasks with our approach with our current DGX cluster is using Q Quantum SDK, right? Q Quantum SDK is primarily built to accelerate your quantum workflow with our current DGX clusters, right? So basically, this is not a quantum computer or a computing framework or a circuit simulator, but this is a SDK which helps you to accelerate your workload, quantum workload in GPU, right? Basically, this is possible through when you're using quantum computing framework like Circ or QZ, you can easily accelerate this workflow with Q Quantum, and then you can accelerate this with GPU computing. Right? That's how Q Quantum comes into play. It's not straight away building a quantum computing framework, but when you're building something on top of quantum computing frameworks, you can accelerate the workflow using Q Quantum on GPUs. That's a brief about intro to quantum computing and how this current generation DGX clusters are helping quantum workloads, and there are huge potential for next 10 to 20 years on how this clusters can be leveraged to accelerate the quantum computing research. I think Q Quantum, we will have a detailed upcoming session in the following week where you can see how this has been leveraged with the example. So we have seen AI SDKs, and we have seen example of LLM and conversational AI with Nemo and Riva. Then we have seen how Q Quantum is used in quantum computing research, especially with the current cluster, how we can use the current clusters to accelerate the quantum computing research. And third, an important piece is Modulus, right? Basically, Modulus is a physics-based, physics ML-based models to simulate real-world scenarios, right? Especially scenarios like weathers and weather forecasting and fluid dynamics, right? One of the primary reason this is more effective in current scenario is earlier all these HPC simulations are mostly simulation workloads, right? But not involvement of AI in it, right? Now with the combination of machine learning and AI into this workflow, we can see huge improvements in performance. At the same time, also trying huge simulation items which is not possible earlier, right? That's when Modulus comes into play, pretty much accelerating all your HPC workflows, whether it's fluid dynamic simulations or whether it's weather forecasting simulation with the real-time scenarios through a simulation engine, right? Basically, one of the primary use case you can see is Forecastnet. Forecastnet is a Fourier forecast operations with ML-based performance, right? That's what this Modulus is offering. Basically, you can easily simulate an environment or create a digital twin of a physical simulations with the tweakings with ML, so that you can simulate the real world scenarios which is not possible earlier with digital twin using Modulus, right? So that is one of the primary reason Modulus is getting traction, because it's a physics and ML informed simulation of workloads. So next, we'll jump on to HPC SDKs. Before that, if you have any questions, you can put it in the chat. I'll take a few questions and we can continue with the HPC SDKs. Cool. I think there are a few questions. I'll answer this. So okay, so you mean the application performance shown in the beginning, it was NAMD? Yeah, it was a NAMD performance. So I can also share the benchmarks after this session for that performance. Yeah, difference between Tau and Nemo, where to use what. Okay, so Tau is a transform, adapt and optimize. It's a transfer learning toolkits. So it also have all the weights for computer vision and NLP models. But Nemo framework is more focused on LLM, and especially for enterprise LLMs for training in large scale and also deploying it, right? So if you're just if you're morely focused on computer vision, you start using Tau models, Tau CV models, weights. But if you're working on LLM, right, so Nemo is the best place to go for. So you have a lot of transform based model checkpoints already available. You can leverage that, and also you have a config files in Nemo where you can just change those config files and scale your workloads across multiple GPUs or multiple nodes. So pretty much, if you're working on CV workloads, try to use Tau. If you're working on LLM, start using models from Nemo. Okay, how many concurrent users are getting served with A30 or A10 for ASR model? So this is depends on the workflow, right? The what is your ASR pipeline is, right? And what model you're using, whether you're using conform or CTC, or what are the specific model you're using. That depends on it. But I can share some reference benchmarks which NVIDIA has with some models, right? You can use it as a base reference, and you can try out with A30 and A10. Okay, so can we use HPC in Windows or Linux? We need. Okay, so all the HPC SDKs in NVIDIA HPC SDKs available in container format. You'll be using it in Linux. It's not effective, or it's not highly supported in Windows. Cool. I think there is no question. I'll continue with the session. So till now we have discussed SDKs on AI and quantum computing, and then on specifically on physics informed neural networks, right? Which is Modulus. Now we'll jump on to scientific computing part, where we'll discuss NVIDIA HPC SDKs, right? So pretty much we are seeing huge adoption of accelerated computing in different areas, right? So all these areas doesn't have right away acceleration frameworks like PyTorch or TensorFlow, right? So for those kind of areas, NVIDIA HPC SDK comes into play, right? Because it offers two things, right? One is development setup, where you have programming models with C++, C, Fortran, and also OpenACC and OpenMP support, right? And also you have a CUDA in place, where you can custom code your backends, right? And then you have a compiler specific to C++, C, and also CUDA, right? And also Fortran. So, and then you have a core libraries like LibQ, Thrust, and Cube, and you have math libraries to accelerate your math operation, algebra, whether it's algebra operation, whether it's a Fourier transformer operation. And you also have a communication libraries which helps you to scale your workloads across multiple nodes. So with HPC development stack, you can pretty much have a common programming models available, where you can program your codes for GPUs or application for GPUs, and you also have a compiler so that you can compile it, and you also use math libraries to run your math workloads, right? And with communication libraries, it's pretty much effective. You can scale your workloads, whether it's a simulation workloads, or it's a custom simulation workloads, or a custom math simulations. You can scale it across multiple nodes, right? This is the development stack. And then we have an analysis stack. So when you're custom creating your backend, or using or building applications using programming models like C or C++, you can easily profile those applications with profilers, which NVIDIA offers, which is Insight System and Insight Compute. And also you can debug the CUDA codes using CUDA GBD, right? So that's what pretty much in terms of accelerated computing and scientific computing. You have already accelerated frameworks available, but if you're still working on problems which needs for you to build a custom backend, you can leverage this programming models, compilers, and communication libraries to custom build your backends. And pretty much with any codes or any HPC or scientific simulation codes you can profile it using Insight Systems and Compute, and you can debug it using CUDA GDB. So next important part or piece of HPC stack is HPC compilers, right? So we have a NVIDIA C compiler, and we have an NVIDIA C++ compiler, and we have NVIDIA Fortran compiler. So if you're working on any of these three languages, it's pretty straightforward for you to port the code and accelerate it using GPUs, right? And we also have NVCC, where you can build your codes with CUDA and you can easily accelerate it using GPUs. So pretty much any GPU, if you're using this compilers, it's pretty much run on automated to run on any GPUs you have. And you have a programmer language where you can customize your backends with specific languages, whether it's C, C++, or OpenACC or CUDA. You can run it on GPUs, right? So pretty much CPU optimized also. You can put it, can be portable across the platforms, whether it's int86 or ARM or even open power. So that's the flexibility this HPC compilers offers. So you can run it in multi-platform setup and also code it using a typical C, C++, or even CUDA stack and build your backends. So we have seen the development stack and the analysis stack and how these compilers are being very useful. Next, we look into the programming, the NVIDIA platform, right? So as I mentioned earlier, so you have Photon, which is GPU accelerator. You have C, which you have C++, you have OpenACC, and you have OpenMP. You can pretty much choose whatever is suitable for your backend and creating your own backend for any specific acceleration, right? Whether you're working on mathematical operations or whether you're working on any quantum or any scientific computing operations which doesn't straight away have a GPU acceleration, you can still use this programming platforms available for you to create your own backend and accelerate it using GPU, right? So with combination of this programming platforms, with these compilers, and with acceleration libraries and profilers, you can seamlessly build, run, test, and optimize your backend code with for GPUs. So we have seen programming the NVIDIA platform. Now we also have a specific math libraries which is already accelerated on GPUs. So if you are working on any similar math problems, you can straight away start using these libraries and accelerate the math simulations in GPUs, right? So starting with QBLAS, like basically for your linear algebra operation, where you can just straight away use the QBLAS. A lot of equations and functions are already GPU accelerated. You can just jump in and start using this, right? And you have a Q sparse, Q tensors for tensor and sparse tensor operations. You have Q solver, and you also have a QFFT for Fourier transformer operations, right? All this is straight away accelerated in GPU. You can straight away start using these libraries and get a acceleration instead of you building your own backend, right? That's the specialized libraries with NVIDIA offers for math operations, and you can get a straight away GPU accelerations. So we have seen all these SDKs, HPC SDKs, whether it's programming layer or it's a compiler or it's whether it's a SDKs, right? The next important section is the communication libraries, right? Because uh, with the current accelerated current complexity of workloads, none of your workloads are mostly single node, right? You have to scale into multiple nodes to make sure you have a faster simulation in place and you can seamlessly scale, right? That's when this communication libraries comes into play. If you're using the earlier SDKs, especially the math libraries or HPC simulation libraries, most of the libraries support multi-node scaling. If something is not supported, you can always custom code your multi-node backend or how this routines can be written, right? For that, you can leverage HPCX communication library where you have a NVSHM and NCCL, right? So NVSHM is basically dealing with how you handle your storage specific to multi-node scaling, and NVCL and NCCL is basically Nickel is dealing with how you handle the process when you're scaling to multiple GPUs or multiple nodes, right? How this multi-node collectives can be handled using and Nickel, right? So it has all reduced, uh, gather gather all these algorithms pre-built. So if you're building a multi-node scaling workload which is not readily available, you can create this backend routines and make sure you can able to scale your workloads to multi-nodes. That's the primary crux of communication libraries. So if you're thinking of PyTorch or if you're thinking of AI workload, pretty much it already offers all this backend. So you can just pull in the required APIs or using the required distributed training APIs to scale it to multiple nodes and multiple GPUs. but with certain HPC workloads, which is not straight away accelerated, right? So you have to build the backend to scale to multiple nodes on multiple GPUs. So on top of it, and nickel also, so NPA also is supported in GPU setup. So you can easily create a GPU accelerated MPI communication protocol where you can scale it to multiple nodes using MPI also. So we have seen communication libraries to scale to multiple nodes or multiple GPUs. Then we'll quickly look into some of the developer tools it offers. You have, right. So one is debugger. So if you're building a CUDA based application or C++ based application and run it on CUDA, you can easily debug it using CUDA GBD debuggers, right? So that's pretty much available on Visual Studio. You can download this plugin and start debugging your code. And when it comes to profilers, you have an Insight system and Insight compute. You can profile your code for multi-GPU workloads. You can profile all your simulation codes or even AI codes for multi-GPU and multi-node workloads, right? That's how we identify the performance gap where you can improve your performance and profile your code and see where you can improve it and try to optimize that so that you can have a best performance out of the cluster or libraries you're using. And you also have pretty much a correctness checker along with this, so you can easily write your code. And you have ID integration. You can integrate it with Visual Studio, you can integrate it with Eclipse or even with Visual Studio Code Edition, right? So pretty much very developer friendly. You can start using this HPC SDKs and develop your backends if you need a custom backend, and all the developer tools required for you to help you to accelerate the development processes available within NVIDIA stack. So till now we have seen the complete brief of NVIDIA HPC SDK stack. So in upcoming weeks we have a detailed session of on this specific SDKs, and where you can get much more deeper understanding of this. Next, we will jump into some of the case studies of DJ SuperPOD across the world, and also specific to C-DAC, how this clusters are used to build a large scale workload and also scale to multiple nodes with seamless integration, right? Yeah, before going here, like I'll spend a couple of minutes. If there is any questions, I'll address it. Okay, there is a question. Can I have a multiple instance of ASR models on same GPUs as we have any? Yeah, you can do that. Like if you have a multi-instance, you have a 800 GPU, you can, or A30 GPU where it has a multi-instance GPU feature, you can obviously deploy multiple ASR pipeline in it. Nemo will support Keras transfer learning. Okay, so Nemo itself is a framework, right? It has a PyTorch and PyTorch Lightning backend. So you can pretty much use transfer learning available within Nemo itself. It need not require Keras transfer learning in place. But the short answer is it's not straight away supported, but it's best to use Nemo framework itself to do the transfer learning for NLP models or large language models. Cool. I think okay, so how to use Python for image processing in HPC supercomputer? So if you're asking in terms of if you're not using any framework like TensorFlow or PyTorch for image processing, then you also have a wrapper for Python to accelerate in GPUs like PyCUDA, similar kind of libraries where you can use to build your own custom image processing backend in HPC clusters. But usually, if it is just image processing with, you can try to see if that is supported in TensorFlow, PyTorch, or even with OpenCV, and try to accelerate it. If not, you can build your own backend. what is the optimal way to train computer vision model using PyTorch Lightning on multi-node setup, right? Yeah, so this pretty much we'll cover in our multi-node sessions, how to train a model in multi-node setup, so that you get a better idea around how you can use PyTorch to do multi-node scaling. Cool. I think I'll continue with the section, and once the session is done, I'll come back to the questions. So next, we'll quickly look into some of the case studies. So if you are using DGX SuperPOD clusters, you are pretty much in a safe hands, right? Because this cluster are well tested for performance scaling without any bottlenecks, right? So pretty much if you see from the customers around the world, what are the customers using this cluster, you can see how effective these clusters are, right? So 9 of the top 10 global universities are using DGX SuperPOD cluster, right? So top US hospitals, 7 of top 10 US hospitals using is, especially if you think of government institutions, 10 of all the government institutions have started using this DGX SuperPOD cluster, right? So pretty much if you think of digital native like computer internet companies like Google, Microsoft, all of them are using DGX nowadays, right? Especially Microsoft, right? For even if you think of ChatGPT, it's been accelerated using the similar kind of cluster, right? And if you think of research institutes, a lot of research institutes have this SuperPOD infrastructure at their place, doing a lot of breakthrough research in terms of HPC workload or even with AI workloads, right? So pretty much well tested platform, and in terms of performance, it gives huge performance leaps compared to other custom built HPC clusters. So you can see this is just to refer that how top companies in specific segments are using the SuperPOD. Healthcare, you can see Pfizer is using it, like consumer internet, as I mentioned, Microsoft, and large consumer internet companies are using it, especially with supercomputing. You can see C-DAC is one of the early adapters in India, like primarily used for larger workloads, and a lot of other top supercomputing labs around the world are using this, right? So pretty much when you think of government or even enterprises or supercomputing lab or research institute, so DGX SuperPOD cluster is a go-to infrastructure to 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 do HPC workloads or even to do scale to multiple AI workloads, right? So pretty much tested, and especially with enterprises, we are seeing huge traction in last 1 year because of the boom in LLMs and how this kind of cluster is required to scale your model to multiple nodes and also deploy it. So as in India, so one of the primary success stories is C-DAC, right? So earlier you had a Paramsiddhi with 40 node DGX cluster. Now we have scaled into AIRAWAT-Paramsiddhi. You have currently 80 nodes, right? And you're gonna keep on scaling this, right? Because of the demand India has, right? So one of the primary example or success I can say is AI for Bharat, right? So C-DAC is supporting AI for Bharat to build a Indic language models, right? Especially building a large language models is a complex task, and you need a specific distributed compute infrastructure so that you can easily scale it and do the pre-training of it, right? And in our Indian context, where we have diversified languages, it's very much important to have these kind of clusters in place so that it helps you to train Indic specific languages, right? So C-DAC is supporting AI for Bharat in a lot of this below use cases and workloads they are working on, whether it's translation, whether it's building a language model or language understanding or speech recognition. A lot of these use cases or research areas they're working on has been trained using C-DAC SuperPOD cluster, right? So it's going to evolve and it's going to scale a lot because we are seeing lots of traction in building language models for Indic languages, and also building lot of use cases, specifically government use cases to build a conversational pipeline with Hindi and other Indian Indic languages, right? So this is going to this C-DAC cluster era with Paramsiddhi is going to accelerate this development and help us to build Indian specific language models and use cases on top of it. So one is we have seen how C-DAC is offering this world's best infrastructure for all the specific use cases, and it's very key here where C-DAC is playing huge role in this kind of provisioning this kind of infrastructure. It is not easily available for any startups, right? This is a huge initiative. At the same time, if you think of enterprises around the globe, they have started adopting this infrastructure heavily, right? Since last 1 year, this has been even more faster because of the LLM workloads, right? Especially with drug discovery, Pfizer, BMS, a lot of the huge companies have started using DJX cluster for their workloads. And you have digital twin companies where trying to build language models and integrate digital twins with Omniverse. And you have industrial inspection use cases across all the top manufacturers, right? And also manufacturers and autonomous systems, they have started using large language models to automate their internal workflow, at the same time build customer facing applications. All this demands a huge cluster kind of setup, so that's where they are trying to adopt DJ SuperPOD and build use cases and scale their workloads across the SuperPODs, right? So if you think of a research, or even if you think of building a production level models and deploying it, SuperPOD is accelerating all these requirements, right? So pretty much end to end, companies are looking at SuperPOD as a primary infrastructure to have to scale their AI workloads, and treating their data center as a single compute unit to accelerate their training, to accelerate their deployment, inference, and also do a lot of simulation workflows, whether it's drug discovery, fluid dynamics, or any digital twin replication. Right? So that's how we can see how effectively these clusters are used, and the success of this cluster is reflecting across enterprises, and enterprises are adopting AI and serving as with all the AI applications. So this is how the pretty much the section is. So we covered the overview of accelerated computing and how it has evolved from 2006, starting with the CUDA introduction, and from 2012 for AI with AlexNet movement. And then we have discussed end-to-end stack of NVIDIA end-to-end ecosystem, and then AI SDK, especially we touch based on NeMo. And then we discussed on HPC SDK stack and what is the end-to-end stack, and we discussed on Quantum, which is specifically meant for helping quantum computing research. And then we discussed on Modulus for physics simulation, right? So this is pretty much for this session. In this upcoming session, we will deep dive into each of the section, whether it's LLM specific workloads, or with quantum computing, or with computer vision workloads. We'll discuss how each of these SDKs can be leveraged and application can be built on top of it, right? So this is the end of the session. If you have any questions, I'll address it for next 10 to 10 minutes. And next session would be on doing a multi-node scheduling in SLURM, and how we can leverage all these resources available using NVIDIA and GC, and we can deploy or schedule a multi-node job in this AIRAWAT-PSAI cluster using SLURM. So if you have any additional questions, you can drop it on the chat. I'll try to address. Okay, I think I have a few questions. So is it possible to do a transfer learning in ASR? Okay, this question is addressed. Yeah, if you have any additional questions on the topics we discussed, please post it on the chat. We can address it.
Yeah, hi Aryant. I guess if there are no questions, maybe we can take 10 minutes break and come back.
Sure. Yeah. Yeah, I think we can take a 10 minutes break, and then next session would be on SLURM, multi-node job scheduling with SLURM. Thank you, everyone.
Yes, great. Thanks, Aryant. Thanks, everyone. We'll come back in 10 minutes. Yeah, hi Abhishek. Am I audible?
Hi Meghna. Hi everyone.
Hi, yes. Yeah, hi. I think you're audible too.
Yeah. Uh, Let me know
Yeah, maybe,
and
yeah,
we can start.
sure. Maybe we can start. I think we had 10 minutes break. We can start now.
Okay. Hello everyone. Welcome to the AI onboarding series of sessions. The topic of discussion is NVIDIA NGC, multi-GPU, multi-node training and profiling. I'm Abhishek Chaudhary. I'm Senior Platform Engineer at Quantify. Will be your speaker for this session. Yeah. So let's get started. So on the agenda, we have the first item, which is NVIDIA NGC. We're going to cover the overview of NGC and the container environment and how to use NGC. Next up, we have SLURM, and then we have Enroot and job scheduling. Uh, Next up, we have job scheduling best practices and profiling your AI or HPC jobs. So, and let's get started then. So NVIDIA NGC. So NVIDIA NGC is a hosting place for NVIDIA software ecosystem and deployable SDKs. It is more likely a collection of containers, pre-trained models, industry SDKs, and Helm charts, etc. We can get a suite of GPU accelerated containers like PyTorch, TensorFlow, Cafe, etc. um, for your uh, AI workloads, and you can get the HPC containers like Chromax as well. We also get pre-trained models in order for you to build your own AI application in a shorter duration. In addition, we also have industry SDKs such as Clara for medical imaging and ISAC for robotics use case. We also have Helm charts for your automated Kubernetes deployment of these SDKs and other frameworks like Triton Inference Server as well. So in a typical DGX setup, uh, we have hardware layer, uh, which is our normal DGX server. And on top of that, we have the host OS, which is the DGX OS as represented in this slide. And then on the host OS, we have NVIDIA drivers running, which are used for communicating with the NVIDIA GPU. And next up, we have container runtime, which could be either Docker or Enroot or Singularity, etc. But to make things simpler, we are using Enroot as the primary container runtime because of its edge over Docker. And we're gonna discuss in detail about Enroot and how is it better than Docker in terms of security and other privileges. So we'll be exploring Enroot, which is used in uh, AIRAWAT-PSAI cluster for Slum usage. And on top of the container runtime, we are running the containers. So what are containers? Just a simple definition for container is these are self-contained software units that include an application and all its dependencies, and it's independent of the underlying OS. So uh, you can streamline the development process, eliminating complex environments in the in this cluster, right? And in the NVIDIA NGC catalog, you'll find GPU optimized containers for various applications, ensuring performance, security, and scalability. The benefits include easy deployment, faster training, universal compatibility, and increased confidence in deployments. So these containers could be of any kind for machine learning, HPC, and deep learning. So let's have a detour and just explore NGC for a bit. So yeah, I'll be resharing my screen. Just give me 1 minute. Yeah. Yeah. So you need to type in ngc.nvidia.com in order to go to this website. And on the left section, you can see there are different sections here, like collections, where we have all the necessary components in order to run an AI task or HPC task. So if we browse through, we can get a different collections here, and it could be related to anything. For example, let's go to HPC collection, and we can find a overview document here. And inside this collection, we have 4 containers. So as you can see in this overview, in this collection, we have different containers like Chromax, NAMD, and other SDKs by NVIDIA itself, which is Index HPC SDK as well. So you can browse through uh, and look at all the collections which are specified, and get started really fast. We can move towards the containers part. So if you can type in like PyTorch, you'll get the PyTorch container here. One second. Yeah, sorry, there was a network issue. So inside this container, you can see there's a download link as well. You can get the container. I'll show you the brief overview how you can download this container as well in the later slides. So yeah, that's how containers are placed inside this catalog. And we can also search HPC containers. We can type in just HPC, and we'll able to see multiple containers like ParaView, Autodoc, Index, KaiPio, and other HPC containers as well. Uh, uh, Similarly, we have Helm charts for Kubernetes deployments, and we have the pre-trained models as well. For example, we have Riva ASR Spanish English language model as well, which is a multilingual model. So you can download this model as well by logging in. So yeah, that was the brief overview. Uh, we will take deeper dive into this in the later slides. So yeah, let's continue. One second. Yeah. So inside the NGC container, in a typical PyTorch container, yeah, we have PyTorch library itself. Sorry. Yeah, one second. So sorry. So in a typical NGC container, where we have a
Abhishek,
PyTorch.
your screen is
Yes.
not visible.
Oh, sorry, one second. Yeah, is it visible now?
Yes.
Yeah. Yeah. So we were talking about this PyTorch container, right? So inside this PyTorch container, we'll find the PyTorch library itself. Then we have the supporting system libraries like CUDA-X libraries and the networking libraries like Nickel, and for multi-node communication, right? We also have utility libraries.
Is there some issue with presenting?
Yeah, whenever I present, I'm not able to switch the slides. One second. And now I'm able to.
Yeah, hi Abhishek. I think your screen is visible now.
Yeah, I'm trying to switch the slides.
We can see clearly that your slides are moving.
Yeah, now I'm able to. One second.
Great.
Yeah, so sorry, so sorry. Yeah, so we'll continue. So we have utility libraries like profiling tools, NSYS, like NSYS, and then we have the Jupyter Lab for development, and TensorBoard for visualization of our models, right? And the containers are updated once a month to add new features and to eradicate issues. We can view the release notes on this link in order to get the idea about the container releases and what are the new features added. So you can view this release notes as well. Can anyone confirm, is the screen visible, right?
Yes, it is visible, Abhishek.
Okay. So in this release notes, you'll be able to see all the releases and what are the versions of PyTorch updated, and all the other, content will be updated here. So you can take a look and get started. Yeah. So to pull a NGC container, like I showed in the NGC portal as well, there was a get container link, and once we have the container link, which is this one, steps to run TensorFlow Docker pull, and then the container link, registry name and the container name and the tag, we will be able to pull through Docker. But yeah, in our environment, in C-DAC environment, we will be using Enroot for pulling the container, which is the Docker container, and running it through Enroot. And this is just an example. If you want to run a Docker container, pull Docker container with through NGC and run it in your environment, you can do it with Docker as well. And you can also customize the container, same container, with with the Docker file, importing that same container, and on top of that, installing your own libraries and other tools. Okay. So are there any questions? Like, I'll be able to take that. One second. Okay. Yeah. Yeah. So let's move ahead with the SLURM. So the question is, why do we need orchestration in the first place. So, and as shown in that slide, we have two scenarios here. In the first scenario, we have nodes dedicated to users for a limited amount of time, and management is done by some Excel-like tools. This setup can be used in a where we have less number of nodes, but in cluster where we have more number of nodes, we refrain to use this setup because it requires user coordination, uh, and resources can go underutilized, where users can block resources for X amount of time, right? However, this setup can work for 1 or 2 nodes, but it's not scalable to something like 50 or 100 nodes. So, and there is one more factor, which is there is no maintainability in this setup. So what we can do to eradicate this problem is we can use a thing called cluster API, which in our case will be using SLURM. So that can give us automatic job scheduling. There is efficient use of resources. It is highly scalable, and there is a standardized maintenance to it. So so that's why we will be using SLURM uh, in our today's session, right? So a typical SLURM software stack, you can see on this slide. Uh, we have usually two different type of nodes. On the right hand side, we have typical SLURM worker node, which consists of SLURM daemon, SLURMD, and other software which is required to run job application. As you can see, we are using entire software stack here, an NVIDIA software stack. We can also run application on bare metal as well, but this is not the case for us. On the left hand side, we have one node for SLURM login, and this is the way to access SLURM cluster via SSH. In fact, you can run everything on the same node in order to run the orchestration itself. So we can view SLURM cluster by SSH into the login node and running job on a compute node. Yeah, we will be using same setup for our demo as well today. Yeah. So Enroot and job scheduling. So as we talked about, Enroot is a container runtime, and why we are using Enroot in our setup, which is AIRAWAT-PS. So we will be discussing more about other container runtime and advantages of using Enroot in this environment. So there are uh, there are issues with using Docker. So we'll be addressing those issues one by one. So when we talked about containers in the previous slides, we talked about Docker as a container runtime. So we need to understand the issues with Docker and how we can resolve them. First, there is a security issue. If users are in the Docker group, uh, they can easily get root access at the node, and they can basically remap root file system, and they'll be routed to host file system as well. Secondly, even with trusted users, root privileges causes escalations with the system admin, which requires system admin intervention as well, such as file permissions, which is a well-known issue with Docker based systems. Also, we have resource isolation, which is a big issue as well. SLURM can run tasks in C groups, which can limit the resources. But when a user starts a Docker container, they have root access now, and they can easily escape the C groups and escape the isolation. So they'll be using, uh, 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 there'll be no limit for using the resources as well in Docker. Lastly, there is a usability issue where Docker is pretty known at this point, but there is a learning curve attached to it. So new users get it's harder to get acquainted with, right? So how we can solve with this with Enroot as a container runtime is we have specific features which has been developed with uh, developed by NVIDIA so that Enroot can get an edge over Docker in a case where we are using where a cluster is being used by multiple users, right? First is the fully privileged CH root. So Enroot provides a fully privileged chroot environment, enabling users to run containers without the need for root privileges. This ensures enhanced security and minimizes potential risks. And it is a standalone system and designed to work independently and efficiently, making it easy to integrate with existing workflows and environments. Enroot offers a lightweight isolation with minimal overhead, ensuring optimal performance while keeping the resource footprint low. Enroot supports Docker images. So in this session also, we'll be going through uh, the slide where we use Docker images and use Enroot as a container runtime to import this Docker image and run that same Docker image in the Enroot environment. So we have a Docker image support as well attached. And then we have a simple image format in the Enroot environment. And it is composable and extensible. Enroot's design allows for easy composition and extension, making it adaptable to various use cases and custom configuration. And uh, in comparison to Docker, it is user-friendly and hassle-free experience for container creation, management, and deployment. Even for new users, I think it'll be there is still low learning curve attached uh, in comparison to Docker. Right? Okay, so these are the simple commands that we can use to import a Docker container from NGC and use it in our environment, right? Which is used to import the PyTorch container from NVIDIA GPU Cloud, where we are specifying a Docker URL and the uh, and
Hi, Abhishek. I don't think we can hear you. Hi, everyone. Sorry for the inconvenience. Let's check with Abhishek and come back. Just give me 2 minutes. Yeah, I guess he'll be back in 2 minutes. So meanwhile, if you all have any questions, please feel free to ask. Yeah, I guess there is just one question which is not being answered. Someone can answer that.
can you hear me now?
Yes,
Can
Abhishek.
anyone confirm?
Yeah, we
Yeah,
can hear you. Yeah,
I'll reshare my screen.
sure. Maybe you can answer the questions later, or if you wish to answer now, you can answer. There are a few questions on the chat.
Okay. Yeah,
I guess you
I'll
can
address
answer.
them.
Yeah, sure. Yes, it's visible, Abhishek. We can see your
Yeah.
screen.
Okay. 1 second. I'm not able to see any questions like after 11:11. I'm not able to see any questions. 1 second.
I guess there is just one question, or maybe it's been answered, so you can continue for now. In case
Okay.
there is anything else, I'll ping you separately.
Sure.
Yeah.
So yeah, can you let me know where I left off so that I can continue from there?
I think. Yeah.
Is this slide done or should I?
Yeah, we can go through this again.
Okay. So this is the uh, this is a slide for basic Enroot usage, like how to import a Docker image from NVIDIA GPU Cloud and create a container out of it in Enroot environment. So there are steps to it. We'll go through one by one. So after you SSH on the login node, you will import the container and you will be specifying the same that image name and tag that you got from the ngc repo. So to reiterate, I'll go to the ngc portal one, right? So we'll go to containers and we'll type PyTorch, and once you go once you see this get container, you'll click on it and you'll be able to copy this whole image tag and image path. Okay, and once we are done, like you can go to your cluster. Okay, yeah. Yeah, so in this slide you can see there's an Enroot import and the same that image name and tag that we copied from the ngc portal, we'll be able to use that same link here. Okay, so how do we use it? Just 1 second. Yeah, so we will type it out like this: Enroot import, and then the Docker colon, then // and then the whole link. But we copied the whole link, but we need to mention just the hashtag in between the image name and tag and the registry link. So nvcr.io, just remove the slash before that and we'll be able to replace it with hash. Just that, and you'll be able to import the same Docker. So once we go to the hands-on section, I'll be able to show you how to import this file and how to run your job in Enroot environment and then in the SLURM environment. So these are the basic commands. So first we imported, then we created a PyTorch container, Enroot container with that same squash file which was generated from that Enroot import command. When we list the containers, we'll be able to see the same name that we gave in the Enroot create command, which was PyTorch. And once we are able to see it in the Enroot list, we can start the container by using this command called enroot start, and there's a flag called --rw which will be enabling read write permissions inside the container, enroot container. And then we specify the name of the container that we want to start, and we can also specify the mount point. So in this example we have shown some directory which we are mounting. So this is home example scripts, and inside that script, this directory will be mounted inside the workspace directory, which is available inside this PyTorch container. And we are also starting a script called python 3 main.py. We can also start a bash script just after that, or we can use interactively by just specifying bash. We can also remove the container by enroot remove and the container name. So these are the few enroot commands that we can use in order to get started with enroot, right? We'll be covering most of it in the hands-on part as well. Yeah, so moving on. We have Pixis. So this is a SLURM plugin for Enroot. So in order to run container with a SLURM job scheduler, NVIDIA developed Pixis to seamlessly integrate Enroot containers and run it in a SLURM job. We'll be using Pixis for major of our hands-on section. So we'll be covering that up. And if you are an existing SLURM user, we'll be having extended arguments for srun, where we get multiple flags in the srun command itself, which is like container name and container entry point. We'll be able to specify all those flags with the help of Pixis. So we'll be continuing with the job section, multi GPU and multi node demos. So common usage of SLURM is with so-called SBatch job script. So this is a sample job script that was written for you to get used to the Pixis environment inside SLURM, right? So this is a typical job where we have specified multiple annotations like job name, which is firstly we have single node example. So this example is meant for running on multi GPU with single node only. So we'll be specifying number of nodes, which is 1, and then we are specifying the partition on the cluster itself. So we are using DGX NP partition, and for the tasks we have only one task per node, right? So we are specifying that as well. We have the CPUs per task as well, which we want to allocate to this job. So we have 4, and then we have the GRAS, which is used to specify the GPUs we want to use. So we are specifying 8 800 GPUs here. So in this format, we'll be able to specify the GPUs as well. Next up, what we are doing is we are running a torch job, which is enabled through torch run, and what we are doing is we are getting the host name in this nodes equals s control show host name. So this line is for getting the host name for the slum job where it has been scheduled. And once we get the nodes nodes host name, we'll be able to fetch the head node IP. So the same node will be getting IP address of that same node, right? Once we get the uh, IP, head node IP, we'll be passing that same in our torch run. So you can see in the srun, we are specifying there is no container entry point. So we are giving the command ourselves. There is no entry point attached. And then we have the container image, which is this quantify NVIDIA practice and then PyTorch. I'll be showing you how to download this image and run it, run the script. So we have this squash file which we imported through Enroot, and then we have the container mounts, like we want to mount our directory DDP training directory to the workspace. So this example shows how to train a min GPT model using data parallelism, and we'll be using torch run for our training. So it's a module by PyTorch, and we can use it for multi GPU and multi node training, right? In the torch run, we are specifying the number of nodes, and processes per node means a number of processes per node. So we have 8 cards. So that's why we are specifying 8 processes per node, right? 1 process per GPU. And then we have the RDZV ID, and these are the parameters for torch run, which we are using at backend. So we are also using the backend, which is our storage of the states, like we are storing the states of our training in this C10D backend. Then we have the endpoint where all the data is being accumulated and ran from, right? So we got the same IP, head node IP. Okay. Screen text is not visible. Yeah, can anyone confirm? Like, is it okay? Okay. Yeah. So once we have the endpoint, like which we got from the above, commands, we can specify the same IP here, where we are accumulating all the training weights and accumulating all the matrices. And once we have all done, we can specify the main entry point script, which is main.py. So this is the basic example for running a single node job. So we can continue with the second script, then we go to the maybe the hands-on part. So yeah, like we showed the example for multi-GPU, the same example can be used for multi-node as well. So for example, here we are specifying the job name like we specified earlier. Then we have the nodes, then we have the partition, and the number of tasks in this case will be 2 because we have 2 nodes. So there is we are running 1 task per node, right? So that's why we have specified number of tasks as 2. Then we have the CPUs per task, and the GPUs will be using 8 GPUs from all the both the 2 nodes, right? And once we are done with that, we'll be getting the head node IP like we got in the uh, section before. So once we have the head node IP from these basic commands, we'll be using same srun command with the different arguments specified, like number of nodes is 2 and number of processes per node will be 8 only. So all the 8 cards from both the nodes will be used in this tutorial. Then we have the same random ID which we generated, and also the backend which we are specifying, and the endpoint as well, which is the head node IP and the port, and we'll be running main script. So this same example can be used for both multi-node and multi-GPU as well in a single node. So let's go on to the tutorial part. If anyone has any question, feel free to drop it in Q&A. I'm referring it. Yeah. Yeah. So if we have no questions, I think we can go ahead with the session. Yeah. So I'm logged into the login node like we talked about. We have 2 basic nodes. One is the login node, one is the compute node. So we are referring to the login node here, and we'll be running our jobs through this node only. So once we are in the login node, we'll be running basic commands. So let's talk a bit about Enroot import and how to import the R container and how to run R script with that, right? So 1 second. So yeah, let's get started. We can always do Enroot help. So we have bunch of different commands here that we can specify. We can use Enroot import, export, list, batch, bundle, create, and exec as well. So we'll be moving ahead with our demo. So we'll be making one directory for that. So we made a demo directory, right? We'll be just moving inside. Okay. Once we are inside that directory, we'll be doing an Enroot import. So this this particular command, we are using the registry which is owned by which is a Docker Hub registry. We're not using NGC registry. So this is like an example you can go forward with. For an instance, let's take an example of NGC as well, because we have already seen the example in the slides. So let's refer to the PyTorch and the same container link, that image tag and path that we copied, we'll be pasting it with the Enroot command. So let's meanwhile it's importing that, we'll be using other tab to do that. So Enroot import and the same command, same link that we copied, and just need to make few changes. Like I already mentioned, Docker, then colon, then hyphen, then slash slash, and after the registry name, which is nvcr.io, we'll specify hash. Okay, it already exists, right? Let's just remove this for now. So this is the basic, like command to import a container, a Docker container, Docker image from the NGC itself. Yeah. So the container that we are going to use for our demo, we'll be running it inside this container which is being pulled right now. But this is just an example to show how you can pull any container, any Docker image from NGC, right? How do we track performance while script is running, right? Yeah. So we'll be showing the demo where we are getting an output of the performance, all the metrics, and we'll be able to see like all the accuracy, loss, everything there, right? So I'll be going through that part just in a bit. Yeah, once we have this squash file, we'll be able to run the SLURM job with this. So next up, what we need to do is we need to create this container, right? So with the same, 1 second. Yeah. So we can either create this container, PyTorch, or we can use the same squash file in our script as well. So once we create it, so it already exists. If we do Enroot list, yeah. So you can see there are two Enroot containers. One is profile, one is PyTorch. So it already exists in our environment, right? So next up, what we need to do is we need to download some files. So we'll share a user guide with you. In those, you can go through the steps that we are using here. The same steps will be replicated in that particular user guide. So this is the command for downloading our scripts, which we use for this demo. So once we do a wget here, it will be able to download a zip, right? Next up, we need to do unzip on this zip file. Yeah, so we got a container called min-gpt-ddp, right? So once we are here, we just need to create a multi-node script that we gone through in the slide. Okay, So first up, we'll do nano, and then we'll create a single node job for now. So I already have it copied. Just in case we want to run first multi GPU, not multi node. Like we'll be running it on single node. So we'll be specifying one for the nodes, right? And then we have the task. So one task per node. So our nodes are one. So and task will be one, right? And then the same process, we are getting the head node IP through these through this bunch of commands. And once we get the head node IP, we can specify the number of nodes inside the torch run as well. Number of processes per node would be 8 because we are running each process on each GPU, and other things would be same. Okay, so this is we're gonna specify the job name for as single node. Okay, yeah. So once you are done with the single node script, you can basically do how to run this script. We can obviously specify s batch single node dot sh. Yeah. So we'll be doing that in a bit. We'll just go through our min GPT, this whole folder that we downloaded. So this is just a example for running a GPT like model on a multi-node or multi-GPU. So you can go inside and view different training parameters that we specified. Like you can view the GPT train config.yaml, where we are specifying the path to the input text, input this input data set, and we are specifying the number of layers, number of heads, number of embeddings in our transformer model, and we are specifying the maximum epochs, batch size as well. So different hyper this parameters that you can tune from this config file itself. So how to define and process? Okay, so inside this torch run, right, you have a flag called n process per node. In our case, we have 8 GPUs, so we are specifying all the GPUs. We'll be running this particular training on all the GPUs. So we have specified 8. So we have that's why we are specifying it here. But in order to get the GPUs inside your in this slum environment, you have to pass a certain flag called gres, which you can see here. So it will be in the same format: GPU colon 800 hyphen SXM4. For 2 GPUs, you can just say 2. Okay. Or for in our case, we'll be using 8. We can also run it with 2 GPUs. Let's just run it with 8 once, and then we can tinker with it. Yeah. So when we specify 2 GPUs here, we need to specify the same here. So the number of GPUs we have, we need to specify uh, on the both things. Yeah, got it. Okay. Okay. Yeah. So what I've done is I have ran this script. So it can be done by this utility called spatch, and then we pass the script. Okay. And you can see there's a info log here, which is submitted batch job with and the ID of the job. So in order to view this ID, we can obviously do sq, and we can if you want to check only your job, you can copy this job ID and just do grep and the job ID name. Okay, I think there's some error. Let's see what is it. Yeah. So yeah, 1 second. Why is it not scheduled on that? Okay, fine. So we have the same script here in my environment, which I've already configured. So let's check the output here only. So what we were talking about is we ran the job script and we got a ID from the same ID SQ. We can grep it and just view the same job. Yeah. So here you can view our job is running on this particular node, and we'll be able to see the output as well. So you can see there's a file created just now, which is SLURM 159239, the job ID, and the extension is output. So once we view it, we'll be able to see what's happening inside. Okay. So so what it did is it took the IP of that same head node, like which we used in this, right, and it took it as master. And we are specifying certain things here, like we have minimum nodes, maximum nodes, and process per node, which is 8. We can also specify limit the GPUs with this flag, the same we used in the single node job script that we use. And as you can see, we are running through epochs, and we are on 247. So Torch Run has a feature where wherever your job failed, it will be able to snapshot that part, and you'll be able to pick up the training from there itself. So I think I trained it till 246. Now it picked up from 247th epoch, and we able to see the train loss and the other metrics here. Okay. Yeah, this was the single node. So we can see there are 8 GPUs being utilized here, and just refer to this part first. So there are 8 GPUs utilized at once, and they were being accumulated through data parallelism, and all the weights are being combined into one model file, right? So yeah, this is the way you can run your single node job. Now moving on to the multi-node. Okay. Yeah. So in this example, in the last example, we have seen a single node job executing executing and taking in 8 GPUs at once, right? Now we need to run, for example, your job is configured in that way. You need to use at least 2 nodes, and you need to performance graph for all the GPUs. Yeah. So you can configure a, a tensor board or a PyTorch visualization visualizer, or you can use weights and biases in order to configure that. But in a setup like this, like we have not done that currently. So we are using you know these kind of command based profiling only. So that's why we are sticking to only certain matrices which we have specified in our program. We can obviously use weights and biases in this case, but yeah, for this demo we'll be sticking to this. Yeah. Okay. So number of nodes we have specified is 2. And tasks per node will be 2. Okay, in this case, because each node needs to execute this one task, which is torch run. Okay, so this torch run would be ran twice on both the nodes. Okay. Oh, so sorry, it will be ran once on both the nodes, and we are specifying the GRAS as well, which is 8. And similarly, we have all the other uh, commands to get the IP of that head node, where we are accumulating all the you know uh, all the uh, metrics from all our training, and we are getting all the results there. So the number of nodes in the torch run we have specified as 2. Number of processes per node would be 8. So this specifies, we need to specify this uh, because we need to use 8 GPUs in both the nodes. So we are specifying this. No, don't confuse it with this end task. So this is different. This is different. This is for internal use inside this torch run, right? And the same other flags could be replicated here. So we can run it. Let's see. Yeah, so it's running. But this time we have used a different partition here, bench P. So you can obviously refer to your system admin, like all the partitions which are. Okay, 1 second. So when we are specifying this task, this refers to the whole srun command inside this particular node, right? So this refers to that. So this will be run on both the nodes, this srun command, the whole command, and number of nodes, that's why we are specifying 2. So n tasks per node would be 1. That's why similarly we have specified 2 tasks on both the nodes, right? So that don't confuse it with the other flag, which is for torch run. Torch run just requires this for the number of GPUs that we are using. We are only having 8 GPUs in one DGX, so we are just specifying 8 here. We can't use 16. Okay, but we have specified number of nodes as 2, so torch run will be able to pick up that. I can show you with the example as well. So we have generated 2 output files. So we'll be checking the latest one. Nano SLURM 40. 1 second. Yeah, this is the latest one that we use. So you can see we have output for both the nodes, because this thing torch distributed has been run twice. Okay, so we are also getting the head IP, head node IP, where we are getting all the we are sharing we are storing the state of our training, right? And this has been ran twice because we have this distributed launcher twice in this output log file. So once you get this running, you'll be able to see. 1 second. Yeah, so we ran a single node job, I think. Because of that, we need to reload that snapshot. So just we'll do that now. So in order to cancel the job, we can obviously do as cancel and then the ID of the same job. So I think the single node job was running on the same environment. That's why it got failed. So let's rerun it again and see the results. Yeah, it's still executing. It's taking a bit of time. I'll just wait for a couple of minutes. Let's see. Okay, I think it ran. Yeah. So sorry for inconvenience. I think the two jobs were running at once and they were writing to the same, snapshot file. That's why it was creating error. So just a little reminder for you all. So this we can see. Uh, so we'll take one epoch, which is 401, right? And we can see there are total 16 GPU used here. Okay, you can view it with only this 401 epoch. I think it's still this one. Let's take another example. Um, yeah, this one. So in total, we have 16 GPUs, 0 to 15, right? So you can obviously see that here. And we have used total of how many GPUs? 16 GPUs and 8 GPUs per node. So it's a multi-node training. Yeah. How to run example 400 CPUs per task on multi-node with GPUs for software like Quantum Espresso. Okay. Yeah. So if you want to run like if you want to specify 400 CPUs per task, I think you'll be able to run it with multi-node only because we are limited to yeah. So we are limited to a certain amount of CPUs on DGX. So you can specify the number of nodes as a multiple of how many CPUs you need, and you'll be able to get that. Yeah. Okay. Yeah. Let's go ahead. The presentation. Any other questions? I'll be able to address that after this. Okay, so I think we can go ahead with the profiling part. So let's continue with the presentation. So why profile your code? When is this useful? First, I'll answer the two fundamental questions, that why and when to profile your code. The key requirement of creating a scalable deep learning application is functionally correct code along with optimized training and inference pipeline. So after creating a functionally correct code, we should optimize the code for underlying compute that we are using. As the deep learning training process could take hours or days, in some cases, to converge completely, right? So if it's an inference pipeline, then outputs with expected accuracy and throughputs are very important. Hence, it's essential for us to understand our code, identify bottlenecks, and then optimize the same. And this can be achieved by profiling our code, finding opportunities and optimizations. When I say optimization, it's not only about latency or throughput. It can be about memory utilization as well. Okay. So when to profile your code? So normally we follow development cycle of analyze, parallelize, and optimize. But even before that, we should ensure that our code is functionally correct and produces acceptable results. Once we have a readable, maintainable version of our code, we can enter this in an iterative loop where first we analyze, then parallelize, and then optimize the code. To analyze the code, we can use profilers to understand the code better, how it is performing on given hardware, and then based on the profiling results, we find places or bottlenecks that can be parallelized on a GPU. For example, it can be a simple for loop, and because of the core limitation of the CPU, we can unroll the loop to a certain extent only. So as even today, CPUs will come with anywhere around 24 to 32 cores, which are utilized by other programs running on the systems as well. And once we parallelize our code, we try to optimize the parameters that we have chosen. I'll talk about that more in the upcoming slide. But to reiterate, we analyze the code, then parallelize it, and then optimize the parameters so that we achieve the equilibrium point in terms of application performance as well as resource utilization. For example, if the end-to-end pipeline is processed in memory, obviously performance would be better, but at the same time, memory utilization of that pipeline would go up. As we want to create an end-to-end optimized application pipeline, thus focus should be on optimize between dimensions so that we get a code that is optimal end-to-end and not optimal at a given point in the pipeline. So that's how profiling cycle goes about. Now we have uh, we we need to find performance opportunities as well. So the tools we are going to talk about here would help us understand GPU utilization as it relates to the model code. Okay, we'll be able to measure the time being spent on various operations in every iteration. There can be two possible scenarios for optimization on a higher level. Either the code is compute bound or the particular module of interest is compute bound, or it can be memory bound, right? Compute bound is basically we are waiting for the GPUs or the processors to complete the processing of the mathematical operations. A type of example of compute bound operation is convolution layers. Whereas on the other hand, if we are waiting for the data to arrive so that the compute can happen, then it's memory bound. Okay. Typical examples within deep learning context can be networking layers like ReLU or batch normalization layers. And during the profiling process, we should look out for these metrics. And based on whether it's compute bound or memory bound, we can effectively fine tune and our hyperparameters during the parallelization and optimization phase. And if it is compute bound, maybe going for a higher end GPU or going for multi-node, multi-GPU would be helpful, right? And if it is memory bound, maybe it's good to check out our networking hardware that we have and the primitives used for the same. So limits of performance optimization. So while we are speaking about parallelization and profiling, it's important to keep in mind an important law called Amdahl's law, stating if you speed up part of your GPU training session, that is GPU work, right? Then the remaining parts that are CPU work will limit your overall performance. Due to this performance preposition, we need to find the optimal balance between both the things like our hardware and the software. Optimization techniques that efficiently work together, right, with the hardware and software. Let's say in the pipeline, we have some math operation and some memory operations. There are few other operations, maybe communication, etc. So if we focus on optimizing our kernels, let's say we achieve an 8 to 16 times speed up, but the other two components are still not optimized, then the overall speed up that we get around is 2 times only. As even though we did an excellent job in optimizing math kernels, the overall optimization is limited to 2 times only. Thus, while looking at profiling, it's always better to have system level view in addition to the kernel level views. And the profilers from the NVIDIA are organized to give both system level and kernel level profiling. Next, I'll try to explain performance analysis at the system and DNN level. So in the deep learning context, if we are training in a multi-GPU or a multi-node setup, then at system level, is the communication between nodes or between GPUs is optimal or not? Whether the primitives that we are using are topology aware or not. For example, uh, nickel NCCL is a topology aware primitive for training our models at scale. So such considerations would come under system level tuning. The final part is the entire pipeline. Uh, we may be focusing on the training script or that code, whereas we might not be focusing on the data pre-processing and the loading component. So that might act as a like a bottleneck for the entire pipeline. We can for that picture we can explore libraries like DALI to accelerate data loading and pre-processing activity. Right from the beginning of the pipeline, all the modules involved in the pipeline are optimized. That's the system level tuning, right? Now coming to the deep learning level, we can classify uh, tuning into two parts: training and inference. In the training phase, the agenda is to bring down the training time, whereas in the case of inference, the expectation can be around latency or throughput. So how we achieve the expectations of each and every phase is something that we need to look at in model level tuning. In terms of the training phase, let me give you a quick walkthrough of how GPU functions. Okay, so first we will be initializing the data in the host, that is CPU, and that would be transferred to the device, that is GPU. So while transferring the data from CPU to GPU, the basic unit of computing in this process is called WOPS, which is basically a combination of 32 or multiple of 32 threads that are being initiated. So it's a best practice to have our parameters as multiples of 32 rather than non-multiples of 32. It could be a batch size or any other parameters. Thus, we should avoid having something like 28 or 31 or 25 and keep parameters in multiple of 32. If we do that, then we occupy all the 32 threads in our WOP. Once the so hence the SMs or streaming multiprocessors, which are part of the GPU that runs our CUDA kernels, will be optimally utilized, ensuring optimized training. Right. This is one aspect, and this can be enforced on batch inference as well, but not on real-time inference. Now coming to the inference phase, we might need to explore options like pruning, quantization, etc. Once we do the pruning, we also need to make sure that our model provides acceptable accuracy. Maybe we need to retrain or fine tune the model if not. So that's how we make sure complete pipeline is optimal on a given piece of hardware. And I keep saying that because profiling is subjective to the underlying hardware. Each and every hardware will have different architectures of GPU, and each architecture has its own design parameters like your L1, L2 cache size, how the hits and misses are handled, and how the memory bus looks like. So it all comes to the design architecture. And then let's move on. So let's talk about the different personas involved in this process. Okay, since this is a machine learning pipeline, where we load the data, pre-process it, and then train it and optimize that particular checkpointed model, and finally host it for inference. This involves multi-domain efforts. Thus, there will be multiple personas involved in this process. So to start with, it will be the researchers who will be working on developing new architectures. Next, there are data scientists and applied researchers who use available model for production use cases. The other folks such as DevOps and MLOps guys will make sure that pipeline is user friendly for each and every person, and at the same time models are served to production and it's used by some downstream application efficiently. So for each and every persona, as the output expectations are different, so are tools accordingly. Okay, so we'll be talking about those tools and technologies. So these are the different profiling tools that target various users and their needs. So Insight Systems and Insight Compute target researchers and developers. Data scientists and applied researchers can use native framework profilers like TensorFlow and PyTorch profilers. And data center monitoring tools like DCGM, NVML is designed for system admins, so we won't be covering that. So Insight profilers are included in all NGC containers that are managed and published by NVIDIA. Okay. Before we get into details of the NVIDIA suite of profilers, let's go over the NVIDIA profiling stack. So Insight systems and Insight compute are built using CUDA profiling tools interface. And NVTX, which is NVIDIA Tools Extension Library, is a way to annotate source code with markers and ranges that would help us to focus on important section of our code. We have NVTX support for both TensorFlow and PyTorch. Uh, Framework native profilers can integrate on top of Insight system, and it calls Insight system to collect profile data and correlate it with the deep learning model. So as a user, you can profile at any level that you might be comfortable with. Now coming to the Insight suite of profilers. Okay. Starting with a quick introduction to each and every profiler available. Insight system, which is basically used for system level profiling. Insight compute, which is used for kernel level profiling. And if there are any graphics workload, we can use Insight graphics as well. And I said we have the options to look at the result through a CLI, uh, as UI won't be used in our case in the AIRAWAT-PS. So we'll be using only the CLI tools, right? The Insight product family has Insight Systems Compute Graphics. Insight System is a low overhead performance analysis tool that is designed to provide insights to developers for optimizing their software. The simplest way to profile with Insight System in a container is to download one of the container from NGC. The workflow to follow is you start with the Insight Systems to get system level overview of your workload. To eliminate any system level bottlenecks such as unnecessary thread synchronization or data transfer, etc. Once you have done that, you proceed to Insight Compute or Graphics to optimize most significant CUDA kernels or graphics workload. Moving on, Insight systems include different collection uh, technologies that enables you to capture system-wide information of a workload's algorithm. Determine uh, what both the systems, CPUs and GPUs are doing, and then export the data such that you can process it directly to help you solve your issues. So we'll be looking at a demo of Insight system as well, so that we get an idea how to profile your code with this Insight systems. And there's one other feature, which is it helps us locate optimization opportunities and reveal information about where and why time is being spent within a workload. And due to the nature of collecting system-wide data, it could be the case that a report contains millions of events and the UI is able to handle it without an issue. On the right, we see snippets of Insight Systems UI. As we see here, uh, gaps can easily be identified when the CPU or GPU goes unused. So we can view CPU core utilization, read state, GPU streams, kernels, memory copies, etc. So as mentioned earlier, NVTX API allows you to annotate the profiler timeline with events and ranges to customize their appearance, like color coding and assigning descriptive names to resources such as CPU threads and devices. That makes our life easier. When library authors choose to annotate with NVTX, users can develop a more complete understanding of end-to-end workflow. We can use NVTX dot annotate annotate decorators as shown in the code block to mark code to be measured with color coding. Okay. As we can view this workload on this Insight system timelines as shown here in uh, purple and red code annotation. To record ANSYS a trace using CLI, we can use the shown command, which is ANSYS profile starts a profiling session. T flag selects the API to be traced. If the force override flag is true, it overwrites the existing generated report. If the stats flag is true, it generates like a summary or statistics of the collection. And the output flag allows us to give a name for the intermediate result file, and you can use the help flag to get more information about any of these flags, right? The annotation themselves have minimal overhead and only capture information when executed with NSYS. Okay. So Insight systems, the event table on the bottom portion can show any row from the timeline in detail. It can be sorted by columns and it automatically filters to the portion of screen shown in the timeline. Clicking on the individual event will be highlighting that event in the timeline. and show all correlations of the event at all rows of the timeline. You can also see a detailed view on any region by right clicking onto it, open the event views, which gives us more details about each process. So this view shows an analysis summary of the profiling session. In a particular, reviewing the project configuration used to generate this report is useful. Information from this view can be selected and copied using the mouse cursor, and we can use it for our detailing. Yeah. In the diagnostic summary, you can see all important warnings. Some of them were generated during the profiling session, while some during the profiling, while some were added during processing and analyzing data in the report. So messages can be one of the following types. It could be informational warnings, or warnings or errors. So Insight system gives the user to ability to include or exclude NVTX events from a particular domain. This can be especially useful if you are profiling across multiple libraries and are only interested in NVTX events from some of them. So NVTX trace is a powerful mechanism that allows users to manually instrument their application. This view shows the time series execution of data loading, forward pass, and backward pass as well. Yeah. So Insight Compute. Let's understand Insight Compute in more detail. So Insight Compute is a tool that gives us detailed CUDA kernel performance details. Once you had identified certain areas in the code where the performance isn't what is expected, using Insight system obviously, then we isolate these kernels and profile them with Insight Compute. Using its integration with Insight systems, you can click on any kernel on Insight system timeline view, and it gives the command to analyze this specific kernel with the Insight Compute. The CLI command is shown here. The flag S to escape 4 kernels, C as invocation details, etc., which are taken care by NSYS to generate the command. Alternatively, you can interactively run and analyze directly through GUI. We can see snippets of the Insight Compute UI on right here. Okay. So when you open a Insight Compute report, each report has a several focus section, and all the data is on single page. The sections are ordered from top level to the low level perspective, where the top level gives you the highest level of utilization and the low level is giving you details at the instruction level. Yeah. So one of the most important sections of the Insight Compute report is the roofline analysis. So it is an efficient way to evaluate your CUDA kernel characteristics and understand potential directions for improvement, or why you can't gain better performance. So from the chart, we plot the floating point through flops per second on the vertical axis and the arithmetic intensity of on the horizontal axis. A roofline analysis reports how close your performance is to set of ceilings. These ceilings are represented by the hardware performance. Okay. Overall, it gives us an understanding of how close you are to the hardware limits itself. And if there is any room for improvement, it's a good way to compare with other architectures. So when it comes to profiling your deep learning code, TensorFlow and PyTorch are popular deep learning frameworks uh, that supports profiling. So TensorFlow TensorBoard profile is shown in the slide. TensorBoard provides visualization and tooling needed for machine learning and deep learning experimentation. We can see the workload performance summary, runtime details, and recommendation for performance improvement as well. Similarly, there is a snippet for the PyTorch profiler view. As we can see, it's a similar interface with workload summary, kernel, and memory information, and also the performance recommendation section. Yeah. So summarizing all the best practices for profiling and optimization, we should keep in mind that most of the acceleration happens in the early stages of workload deployment, data loading, copying, etc. There should be as less as possible data movement or copying from CPU to GPU to CPU to reduce latency and increase efficiency. Also focus on the time consuming block first. For deep learning profiling, run profiling only for 10 to 20 mini batches. Uh, Deep learning training operations are identical for every iteration. Hence, a few are sufficient. Also, use warm-up steps before running profiling and ensure that AMP is enabled if your tensor core usage is 0. Some examples of issues in the deep learning code and their fixes to keep in mind. Okay. Uh, First is the deconvolution. Uh, Deconvolutions have tensor core support and are generally faster than interpolations. So change interpolations to deconvolution layer. Okay. 7 by 7 kernels require much more compute than 3 by 3. So use 3 by 3 kernel instead of 7 by 7. Tensor cores achieve the best performance on layers which have the number of channels a multiple of 8. So use 32 filters instead of 30 for convolutions. All these tips would vary according to the data and the DL network for sure, but uh, it can give you a head start. Finally, just wanted to add a couple of rules to keep in mind for writing a optimal code for your own application and avoid performance issues. So reduce input output inside loops, remove loops, try to parallelize operation as much as possible, use lazy evaluation and iterators whenever possible, and skip execution or stop early whenever possible. And lastly, I've attached a list of resources, products, links, documentation, and the GTC talks to help you learn more about profiling and optimization. Yeah, so let's move to the demonstration of the system monitoring with Insight system. Just give me 1 minute. I'll just set up the environment and we'll start. So let's start. Yeah, on the system, firstly, we need to download the container itself, like we downloaded it on our example before, multi-node example and the other Enroot usage examples. So we'll be using a specific container for this. We'll be using a different tag, which is 22.04 for this demo. So we'll be importing that first. So let's do that. So it'll take some time to import. I think we can skip that part for now. Once we are done with the importing part, we can create a Enroot container with specifying the name, which is profile, with the same squash file that we got from above. Okay, and once we are done with this step, we can obviously view the Enroot container. Is it loaded or not? So we do Enroot list. So we have the profile here, and we'll be able to use that now. So what we are going to do now is we'll start this container and we'll be running it in interactive mode. So we'll be using Enroot for this. So we did Enroot start --rw, then profile bash, right? Once we are inside the container, we will initiate some commands. First, we will uh, download the example that we are going to profile. So we're going to wget and run this command. It is provided in the user guide, and all the details will be specified there as well. So once we are done with this wget, you can do nsys help in order to see if the inside system is present on this system or not, on this in this container or not. Okay, so you can see like we are getting a bunch of uh, commonly used commands here when we do the inside help. And we can also do inside profile help. Okay, so this is the same command that we saw in our slides as well. Okay, so we'll be running our profile on the same code that we downloaded. Okay, so if you want to view the code which we downloaded, it will be like, one second, main baseline nvtx.py. So wget command was used to pull this particular uh, you know code. So it's a PyTorch code, and it is a simple CNN, convolution neural network. We have defined certain layers, and we are using uh, you know train our training pipeline in order to train this model, right? So the data set that we are using is MNIST, and currently the epochs that we are running uh, is 5, and we're going to profile it like how is it working, right? So first first we'll profile it for single GPU, then we'll profile it for multi GPU, and then we can move forward. So in order to use single GPU, we'll just go to this line which is model torch.nn data parallel, and we'll comment this. And we'll be only using this model net.2 device. So we'll be only using one GPU. Okay. So in order to run this particular uh, code to profile, we'll be using this command. So run Insight system profiling and store or print out detailed statistics as well, and wait for 30 seconds, like is specified, delay is specified, and stats is true, and will only profile for 20 seconds, and we'll be specifying the main Python file that we are trying to profile, right? Once we do that, it'll take some time. We'll just wait. So we have specified 5 epochs here. So we'll be running it for 5 epochs. It'll just gather all the push pop operation applied on each layer, and it'll just gather all the information, all the overhead information uh, from the GPU itself, from the system itself. Yeah. We'll just wait for it to finish. It'll take just a couple of minutes more, maybe. Yeah, just finish. So as you all can see, like we have the stats report, and you can see different things here. First is CUDA memcopy host to device, means we are copying data from our CPU to GPU, then memset, like the time taken by the GPU itself, and then device to host. So CPU to GPU, like how much time did it took. So all the reports, we can see how much time it has been taken uh, by each of the operation that was done. So we can obviously view this as a report, uh, that our data loading or our pre-processing, then our model execution, training pipeline execution is taking how much time, and how much our time in percentage is being taken um, to run the full pipeline, right? Okay. So you can like we have the report as well generated, uh, and you can view it in Nsight UI. But since we are not using UI here in this cluster, so you can view it on your local desktop installing this NSYS UI, right? Okay. So next up, we can use the same uh, you know code, which is CNN code uh, for multi GPU as well. Since this whole operation was done on only a single GPU, we can also replace it with the uh, data parallel torch.run data parallel, which uses multi GPU. Yeah, one second. Okay. Uh, so yeah, once we replace it, we can obviously go ahead and execute the same code that we executed at first, uh, and it'll be able to show the same logs for multi GPU as well. Yeah, so there's a question with the timeout issue for initializing processes with multi-node training when using with uh, PyTorch Lightning. Okay, so what's the issue? Can you explain it a little bit? So what's the error or the logs that you have been facing? Any error logs you can attach to the chat will be helpful. And yeah, multi-node training and with the PyTorch Lightning will be covered in the upcoming sessions. So I think you'll get a better understanding there as well. NCCL timeout. Okay, okay. Yeah, we can get back to you on this. Yeah. Aryan, can we take a note on this, and we can probably get logs of that particular error uh, that is being faced? Probably will help him out, I think. Hey Aryan, hello.
Hi, Abhishek. I think I've just noted these. I'll send an email internally, maybe.
Yeah, sure. Yeah, end task is total number of tasks with every node. And end task per node, when you specify that, you can either specify one of these. Okay, so when you specify end task per node, so you'll be specifying per node how many tasks you want to run. So yeah, you can either specify one or first or second according to yourself. I think it'll take some time. So I can show the Insight compute as well, since we are running short of time. Okay, one second. Okay. Yeah, I'll be resharing my screen. Just give me 1 second. Yeah, for the Insight compute, like we discussed, we'll be taking a look at the short snippet that we have. 1 second. So we have downloaded a code called kernel_abc.cu, right? So what this contain is, what we are doing is we have written a CUDA code. This is sample code where we are executing, you know, um, matrix multiplication in the uh, in the CUDA language. And as you can see, uh, in in the low level we have a certain, this equation called thread idx dot x plus block idx dot x and block dimension dot x. So this is a short snippet as an example to show how a kernel is, uh, developed, and how we can profile that kernel, like useful metrics we can identify from the Insight compute, right? So you can obviously start by ncu hyphen hyphen help, which is we can see if the Insight compute is installed, and we can see all the flags associated with it. After that, what we can do is we can compile our CUDA code, which is having 3 kernels. Okay, so once we execute that, we'll be able to get an output file with kernel_abc, right? Uh, then we run Insight compute on the executable with defaults, okay, with the default flags. Once we run it, okay, so what are the metrics that has been shown to us? We can view it here. So we are getting different uh, you know different GPU based the stats. First, we can see DRAM frequency, and then the streaming multiprocessor frequency, how many cycles upon nanoseconds does it took, and number of cycles, elapsed cycles, then the memory usage, in percentage. So we are getting all these stats, and we can obviously tune our code, tune our kernels in that way, that this section, this particular stats are being modified in a efficient way. So we can obviously profile on the kernel level based on the Nsight compute, and we can take a look by profiling with Nsight compute to these stats. So these are the few stats that we got. We can also get you know a single kernel level results as well. In the scripts we have defined 3 kernels, right? So we are viewing only the kernel C stats here. So yes, you can see the same stats being shown for this particular case as well. So yeah, uh, so these are the stats being shown, and also in the similar way that we show in seen in Nsight systems, we can generate a detailed report and we can open it in the UI with this NCU-output kernel ABC NCU rep. So this is the output file that we can see or open up in a Nsight UI, right? Yeah. Yeah, so it has generated a report. Yeah, okay. One second. One second, I think it got stuck. Yeah, so and lastly, I have also attached a list of resources and also documentations. Every resources that I utilized for this particular session, you can view it here. And yeah, and that brings us to the end. I'd like to thank for your time and attention today. If you have any questions, I would be happy to open up the discussion. Yeah.
Yeah, thanks, Abhishek. Maybe we can wait for some time for the questions to be asked.
Yeah. Yes. Yes. You can. Uh, Yes, you can use it. You can use DLProf as well for PyTorch profiling.
Yeah, hi, Abhishek. I don't think there is any questions, or maybe if you want, we can wait for 2 more minutes and then we can close the call.
Sure, Meghna. Yeah.
Yes, I think we can close the call since there are no further questions. So thanks, Abhishek, and thank you, Aryan, for the explanation. So thank you, audience, for the participation. We'll again meet again on 31st July, that is next Monday. So it's going to be again theory and practical sessions. So thank you all for the participation.